Once again, a very good afternoon, everyone. This is the second session of day 4 online gate training program 2022. A lecture on foundation engineering will be delivered by Dr. S.K. Prasad, sir, Professor and Head of Department of Civil Engineering, PUCE. I welcome you, sir.
Thank you. Thank you, Professor Manoj.
Uh, to brief about Dr. S.K. Prasad, sir, S.K. Prasad, sir, is the Professor and Head of Civil Engineering at Vidyavardhaka College of Engineering, Mysuru. He worked for 32 years at Sri Jayachamrajendra College of Engineering, Mysuru, and 3 years at MS Ramaya College of Engineering, Bengaluru. He obtained his bachelor degree in civil engineering from the University of Mysuru, securing first rank and 4 gold medals in the year 1982. He obtained his master degree in geotechnical engineering from IIT Kanpur in 1985 and doctoral degree in 1996 from the University of Tokyo. He was the visiting teacher in the year 2000 from Indian Society of Technical Education, New Delhi. He was a visiting assistant professor at Asian Institute of Technology, Thailand, in the year for January 2006 term. He has published over 175 technical papers in national and international journals and conferences, guided over 70 master dissertations, and guided 3 doctoral students. Presently, 3 more students are working for PhD under his guidance. He has completed several sponsored research projects from JSSMFE, ASCTE, and DST. His areas for research interest include earthquake, geotechnical engineering, and performance-based design. Now, over to you, sir.
Thank you, Professor Manoj,
Thank you, sir.
for the nice introduction. So, I'm into my second lecture. Uh, if we try to recap what I covered in the last lecture, it was basically about bearing capacity. I also mentioned to you that geotechnical engineering is one subject which is the favorite of question paper setters in GATE. And in geotechnical engineering, what dealing with now, shallow and deep foundations, including bearing capacity, is one very important topic where often you'll have lots of questions. Keeping that in mind, I started with bearing capacity of soil, so so that we'll prioritize based on the popularity of the lectures. So permit me to share my PPT and I hope I am both audible and visible. And Manoj can let me know if everything is okay. Yeah. So, as I said, I'm into my second lecture of foundation engineering. Just thought I should tell you that, soil is the most complex construction material. What do I mean by complex? You know, if I give you a steel rod, and ask you, can you tell me how much tension it can take? You may be able to calculate a bit and tell that this is the amount of tension it can take without much difficulty. Maybe if I give you a concrete block and ask you to find out how much compression it takes, you would see this, and maybe you will ask what grade, what's the proportion in which the aggregates and then the cement is put. Probably you can guess. It is next to impossible to guess how much is the capacity of soil for various reasons. I have just listed many of these, points which make it very complex. It is porous, inhomogeneous, anisotropic, so many things. Yet, I always say soil is a very smart material. Soil is an intelligent material. What is the proof? I just try to mention that soil is colorful, it is sensitive, it has memory, it changes its properties with time. These are some properties which match with those of human beings. Therefore, it is a material with life. It resembles human beings, therefore it's a material with life. And hence, you cannot abuse soil. If you abuse, it will be angry on us, and it shows its anger in the form of failure. So, it is always necessary for us to learn how soil behaves. What are the factors influencing its performance? So, with that, I just would like to go further to what we dealt with in the last class. I told you that bearing capacity is a very important factor, important parameter used in the design of foundations. I said that, bearing capacity is a simple word, but it is preceded by some prefix. Ultimate bearing capacity is the maximum pressure soil can take at the foundation level. And any extra pressure you apply, soil will fail. We always express bearing capacity in the units of pressure, kilonewton per meter square, megapascal, and so on. Net ultimate bearing capacity is, in case you find bearing capacity at a depth of 1.5 meter below the ground level, up to 1.5 meter. So, overburden was already existing. Now you have removed. So, net ultimate bearing capacity is the maximum pressure minus the overburden pressure. And hence comes safe bearing capacity, which is a very important parameter in the design of foundations. It is the safe extra load or extra pressure soil can take in addition to the overburden pressure. Therefore, you are going to apply for the net ultimate bearing capacity a factor of safety, and normally a factor of safety is of 3 is desired, plus the overburden pressure. So you don't apply factor of safety to overburden pressure because it was already taking that. So whatever extra load or extra pressure it can take, only for that, you're going to apply the factor of safety. Please note, in all these 3 cases, we talked about failure. But then, just like concrete, wherein you have limit state of collapse, limit state of serviceability, even in soil we have limit states. One limit state is failure related, and another limit state is, settlement related. You can't have settlement beyond permissible limits. Therefore, we use the other terminology called allowable bearing pressure, which takes into account both the shear failure and permissible settlement limit. So, whichever is smaller is considered. And this equation I already dealt with in the last class. I told you that, excuse me, QF stands for ultimate or bearing capacity, F for failure. It has 3 terms. First term involves with cohesion, second term involves with overburden pressure, and the third term involves with, the, soil just below the foundation level, the performance of the soil just below the foundation level. So in these 3 terms, you have non-dimensional factors NC, NQ, and gamma, which are simply functions of phi. Phi is the angle of internal friction. When phi increases, NC, NQ, and gamma increase. Then safe bearing capacity QS is equal to net ultimate bearing capacity, what you see here, divided by factor of safety plus the initial overburden pressure. I dealt with these 4 important factors which influence bearing capacity, which Terzaghi recognized, Terzaghi identified way back in 1940s and 50s. He said that, mode of failure influences, though he derived his theory, his formulation, assuming the soil to be subjected to general shear failure. He then gave modifications to shape of the foundation, though the derivation considered stiff footing because he wanted to make it 2-dimensional. Then he considers the effect of groundwater table to be considered. And in the initial case, when the derivation was done, it was assumed that groundwater table is at great depth, therefore there is no interference of the water to the foundation. However, he later on showed that the effect of presence of water near the footing is to reduce the bearing capacity. Then the derivation was done considering concentric loading, but then there are occasions when a foundation may be subjected to eccentric loading. So he gave the modifications, he gave the changes which can be applied to the regular equations if you want to consider eccentricity in the loading of the footing in both the directions. So very clearly, effect of eccentricity is to reduce bearing capacity. Effect of groundwater table being in proximity to the foundation is to reduce the bearing capacity. Shape has some effect, rectangular, circular, square, footings, show some differences. Mode of failure, generally, general shear failure is failure which happens, without any warning. It is generally seen in soils which are dense, stiff. It is generally seen in a situation where the foundation is shallow depth. On the other hand, punching or local shear failure is seen in cases where you have the foundation going deep and in softer soils, in soils which are loose. These are the four equations, we arrived at for different types of foundations. I want you people to remember for stiff footing and for circular, square, and rectangular footing, only coefficient is changed. Second coefficient remains the same in all the cases. First coefficient, it is 1.3 multiplied by 1.3 in case of square and circular footings. And the third component is reduced. 0.3 times instead of 0.5 times for circular, 0.4 times instead of 0.5 times for square foot. But I want you people to keep this by heart. Okay. With this, I will solve as many numerical problems as possible, which I have taken from previous gate, editions. Okay. And as I told, in geotechnical engineering, maybe 90% of the questions are problem oriented. Let me read the question. A 3-meter wide stiff footing, okay, is founded at a depth of 2 meters below the ground surface. Okay. Let me see whether I can try to draw. So this is the footing, strip footing, which is 3 meters wide. It is founded at a depth of 2 meters below the ground level. Water table is at 5 meters below the ground level. See, this is where water table is existing. At 5 meter means, 3 meters below the base of the foundation. Soil properties are given, C is given, you have phi, and please note you are given gamma sat as well as gamma bulk. Saturated density is bulk density when the soil is fully saturated. Okay. Naturally, general bulk density is lower than the saturated density. At this depth, below the ground, below the foundation, is the soil saturated? No, normally no, unless it rains heavily or maybe when the water table rises up. It is said that water table is at 5 meter below the ground level or 3 meter below the base of the foundation. Therefore, no chance for saturation to happen. So it is more rational to consider gamma bulk. Okay. The values of bearing capacity factors are given here. The values are given here. Okay, these are the values which are given. Use Terzigi's bearing capacity equation. Take factor of safety as 2.5 and find the safe bearing capacity. Okay. Please note, I'll have to tell you here that phi is 26 degrees. If you recollect, When phi is 28 and lower than 28 degrees, more or less you can consider that it is local or punching shear failure. On the other hand, when phi is more than 36 degrees, more or less it is confirmed that it is general shear failure, because it is dense. Between phi equal to 28 and 36, it is very difficult to say. When it is close to 28, like 29 degrees, 30 degrees, maybe it behaves more like local shear failure. When it is close to 36 degrees, like 35 degrees, maybe it behaves generally like general shear failure. In between, so we just decide to linearly interpolate in between these. Now that phi is 26 degrees less than 28 degrees, it is local shear failure. What should you do? Whenever phi is less than 28 degrees, reduce the shear parameters. What do I mean by reduce? Don't use the actual value, you use a reduced value. So what will you do? You're going to have C dash, that is the value which you use, which is equal to 2/3 of C. Whatever C is there, 2/3 of that. C is 30 kilonewton per meter square, and hence 2/3 of 30 is 20 kilonewton per meter square. Then phi dash. So tan phi dash is considered to be equal to 2/3 of tan phi. Please note, it is considered to be equal to 2/3 of tan phi. That means, you find out tan 26 degrees, find the 2/3 of that, and then, find the tan inverse of that value. That gives you phi dash. You get phi dash as 18 degrees. And hence, for phi dash equal to 18 degrees, use this table. In this table, for 15 degrees it is given, 20 degrees also it is given. So for 18, you linearly interpolate between these two. And hence, for instance, NC term, NC will be equal to, if I just take NC, let me just try to work out the first one. NC is equal to, for 18 degrees, it is 13 plus, 18 minus 13, okay, into, that is, into, the difference is 15 to 18, 3 degrees, divided by, the difference between 20 and 15 degrees is 5. So that gives you the value of NC at 18 degrees. Likewise, you do for NQ and N gamma, and this is the result you have got here. NC is 16, NQ is 6.8, and N gamma is 4.2. All other terminology is known, you find out the safe bearing capacity. And you find that QS is equal to 293. Please check the answer. So whichever is the closest to that. Sometimes, rounding off, you may have small difference. And you notice that, this is 293. Therefore, this is the answer. So this will carry about 2 marks. And hence, you should be able to do it in quick time. And I took some time to explain to you, but the moment you read the question, you should be able to quickly work out and get the answers. Let me go to the next question. A square footing of 2 meters inside, so it is a square footing, so 2 meter by 2 meter, is placed at a depth of 1 meter in a sand deposit. So few things I want you people to understand. One is, it is sand deposit. So it is placed at a depth of 1 meter. Its side is 2 meters. Footing has an ultimate bearing capacity of 800 kilopascal. QF is equal to 800. Consider the depth factors dq, d gamma equal to 1. You, at this point of time, just forget it. When we use Terzigi's bearing capacity theory, this is not required. Okay. Fortunately, the values are given as 1. If it were to be given as different from 1, it cannot be more than 1, it will be less than 1. If it is given to be different from 1, we have to be bothered. But at this point of time, don't worry. So, and you are given n gamma here. Secondly, now there is a new footing, a new square footing. There's also fortunately square footing having a side of 3 meters and depth of 2 meters is proposed on the same soil. If factor of safety is 3, find the value of the new, find the value of SBC. Please note here, if you want to find the SBC, you should know NC, NQ, and gamma. In this case, N gamma is given, NC and Q are not known. Fortunately, you know that it is sandy soil, therefore NC will be 0. Okay, because C is 0. So to find NQ, you use the data which is given for the initial foundation. So according to that, this is the equation for ultimate bearing capacity for square footing. Initially, you know that C is 0. Therefore, this first term will be 0. QF is 800. B is given 2 meters. Depth is given, which is 1 meter. Gamma is given and N gamma is given. Everything is known here except NQ. You find out NQ. You find out NQ. Where is that? Yeah, I have found here NQ. That NQ is 34. Now that you know NQ and gamma, of course, NC is 0. This value NC is equal to 0. You apply for the second foundation. In the second foundation, factor of safety is given 3. Width is given as 3 meters. Depth is given as 2 meters. Therefore, you find the safe bearing capacity as 510.67. So that's the answer. I then move on to the third question. I just start, as many questions as possible I should solve. And I want you people to solve by yourselves. Then only you get a feel of it. Net ultimate bearing capacity of a footing embedded in a clay stratum. I want you to read the question carefully. Please note here it is mentioned as clay stratum. So when it is given like this, you assume that it is pure clay. Okay, strictly it may have cohesion, it may have friction, but whenever it is mentioned, they could have mentioned as pure clay stratum, but then whenever it is mentioned like this, assume that it is pure clay. When it is pure clay, phi will be extremely low. You can even assume it to be 0. It's only a cohesive soil. So what is net ultimate bearing capacity? Ultimate bearing capacity, QF. Ultimate bearing capacity is known. So QNF I will call net ultimate bearing capacity. It is equal to QF, ultimate bearing capacity, minus the overburden pressure gamma D minus gamma D. So it says net ultimate bearing capacity of clay stratum. You have to choose one of the 4 answers. Does it increase with increase in depth of foundation? So this is the value. Does it increase with increase in depth of foundation? Please note, again I go back to the equation. Do I have the equation here? Maybe. Okay, any footing, it can be strip footing also. Please note that NC is 0. Okay, I'm sorry, NQ and N gamma terms are N gamma is 0 and NQ is also a very small value. You can almost neglect it. Okay, or NQ is equal to 1 for that matter. So QF is equal to 1.3 CNC plus gamma D. QNF is equal to 1.3 CNC. So the answer here is QNF, net ultimate bearing capacity. QNF is equal to just 1.3 times CNC. Okay. So what happens to this? It is independent of both depth as well as size of the footing. So answer, I have written A here. Strictly it is not A. You'll have to cancel this and you have to consider it as D. Because QNF, if you ask ultimate bearing capacity will also have gamma D. If you are considering ultimate bearing capacity, then it will be the presence of gamma d. Then it increases with depth. Since the question is net ultimate bearing capacity, the answer is not A, but answer is D. So in pure clay, n gamma is 0, you should remember, and nq is equal to 1, you should remember. So questions sometimes will be very tricky. I want you to understand carefully. Let me take you on to one more question. So as many questions as possible, if you solve, your confidence level will boost. Please understand, a 4-meter wide stiff footing. So carefully you should know width, and it's a stiff footing, is founded at a depth of 1.5 meter below the ground surface in a C5 soil, as shown in the figure. The figure is shown in the next. Okay, 4 meter, 1.5 meter. And here, NC and Q and gamma terms are also given for different phi's. The water table is at 5.5 meter below the ground surface. Remember here, see here, water table is at 5.5 meters, or it is at a depth of 4 meter below the bottom. Therefore, water table is not interfering here. Basically, you should assume that water table has no effect on the bearing capacity. Soil properties are given. C is known, C is given, phi is known. Please note, it's marginally higher than 28. So you can assume that it is 28. You can be on the safer side. You can assume that it is local shear failure. And then, gamma sat is given, gamma bulk is given. Naturally, you need to consider gamma bulk here also. Because, water table is at a far off depth. The values of bearing capacity factor phi dash are given below using Terziki's bearing capacity theory, and with F is equal to 2.5, you are asked to determine the net safe bearing capacity. Please note here, net safe bearing capacity. Safe bearing capacity is QS. Okay, taking the value of overburden pressure. Net safe bearing capacity is QNS is equal to QS minus gamma D. QS minus gamma D. So expressed for local shear failure of soil. So here itself, indirectly it is mentioned, you have to consider it as local shear failure. So please see here, width is 4 meters, depth is 1.5 meters. C dash is 2/3 of C. C was 35, so C dash is equal to 35 by 3. C dash is equal to 35 into 2. 2/3 of C, which amounts to 26.67. Phi dash is equal to, like before, tan phi dash is equal to 2/3 of tan phi. 2/3 of tan phi. From that, you get phi is equal to 20 degrees. Gamma, don't take saturated density. You have to take bulk density, because water table is at far off depth. B is known, D is known, and for phi equal to 20 degrees, directly you can use these values to find NC and Q and gamma. All things known, you need to determine. What are you asked to determine? Net safe bearing capacity of soil. Net safe bearing capacity is QNS is equal to QS minus gamma D. And you get the answer as 322.3. Therefore, B is the right answer. Friends, this is how calmly you can take the questions. I have decided to solve as many questions as possible so that you understand the kind of questions which you get in GATE. Not very different, whatever you have studied in your undergraduate career using, standard textbooks should be good enough, because, basically what they are testing is your fundamental capacity. Let me then move forward. Question number 5. A square footing 4 meters inside is placed at 1 meter depth in sandy deposit. Please note here, it's a sandy deposit, and at a depth of 1 meter. It's a square 4 meter side. Dry unit weight of soil is 15 kilonewton per meter square, per meter cube. The footing has an ultimate bearing capacity of 600. So this you don't have to bother now. dq d gamma. Bearing capacity factor n gamma is given. Oh, it's exactly similar to the second problem I solved. A new square footing of say 2.5 meters is to be placed at 2 meter depth. Taking factor of safety as 3, find out the bearing capacity, safe bearing capacity using Terzigi's rule. So like before, first thing is to find out NQ. So from the first data, everything is known, including N gamma. Therefore, C is 0. Therefore, NC effect doesn't come into picture. And hence, you have to find NQ because QF is known. Ultimate bearing capacity is known. Then, knowing NQ, for the new footing, you find out the safe bearing capacity. So safe bearing capacity is found to be 222 kilonewton per meter square. Friends, let us go to the next topic. Next question. Width of a square footing and diameter of a circular footing are equal. Width and diameter are equal. If both the footings are placed on the surface of sandy soil, okay, if both of them are placed on the surface of sandy soil, please note, sandy soil, therefore C is 0, first term vanishes. If they are placed on the surface, depth is 0, second term vanishes. So, ratio of ultimate bearing capacity of circular to square footing. Okay, please note, circular footing, if you go back, QF is equal to, let me just show you that equation. I want you to remember that. Okay, circular footing, all these things are, so first term is not there, second term is not there. QF is equal to 0.3 gamma B and gamma. Square footing, QF is equal to 0.4 gamma B and gamma. In both circular and square, the value of B remains the same in this problem. The diameter and the side, they remain the same. So accordingly, QF for circular footing is this, QF for square footing is like this. 1 divided by 2 will give you 3 by 4 as the answer. Therefore, the answer is C. Answer to question number 6 is C. Now let's go to question number 7. What does it say? Percentage reduction in bearing capacity of strip footing. Please note, strip footing. So you know the formula. The formula I have written down here. For our convenience, I have written down the formula here. This is the formula for the strip footing. Resting on sand. Okay, footing is resting on sand. Therefore, this is 0. Under flooding condition, at whatever depth, so the soil is flooded. When soil is flooded, it is in saturated condition. So when compared to situation where water level is at great depth, so whenever it is flooded, please note that RW1 and RW2, both of them, what happened here? Both RW1 and RW2, both of them are, whenever it is flooded, the value is 0.5. That is when the soil is flooded. On the other hand, when soil is in dry condition, okay, under normal circumstance, the value of RW1 and RW2, both of them will be 1. So QF, when it is dry, will be gamma D and Q plus 0.5 gamma B and gamma. QF, when it is flooded with water, will be 0.5 gamma D and Q plus 0.25 gamma B and gamma. Therefore, please read the question carefully. The reduction in bearing capacity when it is flooded, when compared to situation where water level is at great depth, is 50%. So answer is C. When water table is at great depth, RW1 and RW2, both of them are 1. On the other hand, when it is at the surface, the value is 0.5. Anywhere in between, groundwater table is anywhere in between, it will be somewhere in between also. So the effect of groundwater table is to reduce bearing capacity, and when the groundwater table is at the ground surface, there is scope that bearing capacity can decrease by 50%. Friends, let's move on to the next question. A strip footing is resting on the surface. Please note, it is resting on the surface. So depth is 0. And it is a pure clay. It is pure clay. Therefore, second term, third term vanish. You don't have to consider second and third term. Okay. So this is not there because depth is 0. And this is not there because, it is pure clay. So QF is equal to CNC for strip footing. Ultimate bearing capacity of the soil, okay, when the width of the footing is doubled, what happens to ultimate bearing capacity? Will it double? Will it halve? Or will it remain the same? Or will it become 4 times? The equation will now be only this much. This is not influenced by the width of the foundation. Therefore, it remains unchanged. You'll have to write that it remains unchanged. So, if you have understood the concept, solving any problem in bearing capacity is no difficulty. So, as per the syllabus, you should know Terzigi's bearing capacity theory and then Meyerhoff's bearing capacity, which I start, in the next couple of slides. Okay, only these two. Okay, let me try to answer this question. Net ultimate bearing capacity of the footing. Please note here, net ultimate. Net ultimate is QNF, let us say, is equal to QF minus gamma D. Remember this. Okay. QF is given by this. QMNF is QF minus gamma D. Okay. Does it increase with depth of the footing? This is in clay, pure clay. Okay. In pure clay, okay, this term will be 0. And NQ will be 1. Therefore, QF is CNC plus gamma D. QNF is QF minus gamma D, which is simply equal to CNC, which is equal to CNC. Does it increase with depth? No. Whereas QF increases with depth because gamma D is there. Does it increase with size? No. Does it increase with both depth and size? No. It is therefore independent of depth and size. So QNF is only a function of CNC. Therefore, it is independent of depth, independent of size of the footing. So this can happen only in pure clay. If it is C5 soil, it increases with depth, it increases with width. Purely sandy soil, it very much increases with both depth and width. So in sandy soil, it's always good to have the increased width of the foundation and increased depth also. So with this, let us move forward. Let us try to consider Meyerhoff's bearing capacity equation. As I told earlier, sometime in 1940s, 1943, Terzaghi developed his equation for bearing capacity. We'll have to appreciate because, at that time, it was more out of intuition. People started working on bearing capacity and then did some experimental work. People realized that it's very, very important to know bearing capacity properly. Lot of scientists worked since, 1960s, 70s, even 80s. Brinch Hansen, Meyerhoff, Wesig, Bala, several people, okay, and brought out that it is not just 3-4 factors which Terzaghi mentioned which are influencing bearing capacity. There are few more. So we started putting our thought towards generalized bearing capacity factor and capacity considering many factors. So what Meyerhoff said was, you use one single equation for everything, and hence, he said you consider the, shape of the foundation, the depth below, and then, inclination of the load. And hence you have coefficients for these three, for the first term, second term, as well as the third term. This is what Meyerhoff said, and this is what many others also said. Wezik, in fact, said it is not only the load inclination you have to take, you need to consider the inclination of the base of the foundation. You may also have to take the inclination of the ground. Okay. So this is what, Meyerhoff developed, and hence he proposed equations. Terzaghi could not give the equation, especially for n gamma term, he said it is dependent on passive pressure. So it was difficult to give equation, whereas, Mayer have provided the equations for NC, NQ, N gamma. Likewise, he provided equations for finding the shape factor, depth factor, as well as, inclination of the load factor. Please note, Terzaghi's bearing capacity theory is applicable for shallow foundations only. For deep foundations, it is questionable. Whereas, Meyerhoff's equation can be used even for great deep foundation, because, you just take that factor into account. So these are the formulae to be used, and anything in the form of question, if it is to be given in GATE, these are the equations which you don't have to memorize, and these will be given to you. So here terminologies: C is cohesion, gamma is unit weight, D is depth of foundation, B and L are width and length of foundation. Sometimes, you can use them interchangeably. Generally, the lower of the two is width, and Kp is the passive earth pressure coefficient, which is equal to tan squared 45 plus 5 by 2. And then alpha represents the inclination the load makes with respect to vertical. So if it is a vertical load, alpha is 0. If it is a horizontal load, alpha is equal to 90 degrees. So you apply here to find shape factors, 3 number, depth factor, 3 number, and then, load inclination factor, also 3 number. Okay, I just want you to remember the, the parameters, the bearing capacity terminologies which I have dealt with. Ultimate bearing capacity is QF. Then you have net ultimate bearing capacity, which is QF minus gamma D. Safe bearing capacity is QF minus gamma D by F, where F is normally, if nothing is said, it is 3. It will not be less than 2. And then gamma D plus gamma D. And net safe bearing capacity is whatever QS minus gamma D. So it is definitely in the increasing order. The value of QF decreases. QF is maximum, value of bearing capacity decreases. For ultimate bearing capacity QF, the value is maximum. Net ultimate bearing capacity, it will be just less than that by a term equal to gamma D. And safe bearing capacity is approximately, F times smaller than ultimate bearing capacity. If F is equal to 3, factor of safety is 3, it is approximately 3 times smaller. And net safe bearing capacity is the lowest. You should know that. Let us move forward. Okay, I just have a question here. We have solved many of these types of questions. Increase in any of these decreases the bearing capacity. Okay, increase in any of these decreases the bearing capacity. You take the first one. So increase in size of the footing. If you increase the size, will bearing capacity decrease? No. If it is clay soil, no change. But if it is sandy soil, if you increase the size of the footing, naturally bearing capacity increases. Next, let me go to depth of footing. Increase in depth of footing. You go deeper and deeper. What happens? Bearing capacity increases. Why? Bearing capacity equation is a function of depth. Please note, in these equations, we assume that soil is homogeneous. But strictly, if you look at in nature, usually you go deeper and deeper. At one particular depth, you may get hard rock. That bearing capacity increases because soil is more confined, it may get converted into rock and so on. But in this case, even if it is not converted into rock or so, it is just because of the depth factor, because of the confinement, bearing capacity increases. What about shape? Shape changes bearing capacity, but there is nothing to say whether it increases or decreases. Marginal change will be there. And hence, increase in eccentricity decreases the bearing capacity. If the column loads are concentric near the center, bearing capacity is going to be perfect, more, but any eccentricity is going to reduce the bearing capacity. Therefore, the answer expected is D. This is how I want you people to solve problems. Okay. Now that we have solved several of these problems, remember that these are all the parameters which may change bearing capacity. I am now considering C5 soil. I am not considering purely cohesive. I am not considering purely sandy soil, cohesionless soil. So in C5 soils, when you increase the width of the foundation, the bearing capacity increases. When you increase the depth of foundation, bearing capacity increases. When you increase the value of friction angle phi, NC, NQ, and gamma increase, therefore bearing capacity increases. You increase cohesion, bearing capacity increases. In general, increase C, increase phi, both help you in increasing the strength of soil. When the strength of soil increases, bearing capacity has to automatically increase. What happens to water table effect? I always say that presence of water is the worst enemy to geotechnical engineer. Presence of water in ground, it reduces bearing capacity. Bearing capacity may reduce to even half. So it decreases bearing capacity. Unit weight, density of soil. More the density of soil, bearing capacity increases because bearing capacity is a function of gamma. Second term and the third term depend on gamma. Also, strictly speaking, when density increases, automatically phi also increases. That is indirect, additional thing you have to consider. Mode of failure also has an effect. In general shear failure, the failure is catastrophic. But in local or punching shear failure is gradual. So normally, mode of failure also has a big effect. Very difficult to say whether it increases, decreases, under what situation. Therefore, I have not put anything here. Then you have shape of the foundation. I have not put anything because shape of the foundation changes bearing capacity. But sometimes it may be slight increase, decrease, not much. Eccentricity, load eccentricity. Okay, load eccentricity will decrease bearing capacity. Inclination of load. If the load is vertical, bearing capacity is maximum. But if it is inclined, it has horizontal component, bearing capacity will decrease. Inclination of ground will also cause a decrease in bearing capacity. Base of the foundation, if it is inclined, that also will cause a decrease in the bearing capacity. So all these will influence the bearing capacity. What about height of the structure? It should not have any effect. Any kind of structural behavior, at least should not affect the bearing capacity equation. So it's not affected. So friends, I want you people to really understand that bearing capacity is a very important terminology which depends on all these factors which I have mentioned. Keeping that in mind, consider the extreme cases. Purely cohesive soil, purely cohesionless soil. In purely cohesive soil, phi is 0. In purely cohesionless soil like sand, C is 0. Okay, let us move forward. Let us go to the next question. A square footing is subjected to an inclined point load as shown in the figure. Please note, it is subjected to an inclined point load. Water table is located well below the base of the foundation, so there is no effect of water table. Considering one-way eccentricity, eccentricity can be in both directions, but only one way. Net safe bearing capacity, net safe load carrying capacity or safe bearing capacity, that is QNF. For a factor of safety of net safe bearing capacity, that is QNS. Okay, for a factor of safety of 3 is what? The following factors may be considered. NQ is given, N gamma is given. Please note that NC is not given. Is it mentioned anywhere that it is sandy soil? No, it is not mentioned, but it's not given. Then you're given shape factor, you're given depth factor, you're also given inclination factor. You use in the regular equation. Okay, and nothing is mentioned about C, therefore you assume C as 0. So you just have to add the effects of shape, depth, and inclination for the second and third term. It is net, therefore QF minus gamma D by F. So substitute all of these, and hence you get the answer. So did I put the answer here? No, I have not put the answer here. You find out the answer. So it's a direct problem. You just have to write down the equation and properly understand that first term is not there. For second and third term, all other things known, you find out the value of net safe bearing capacity. Let us move to the next question. A strip footing is resting on ground of a pure clay bed having undrained cohesion of Cu. Ultimate bearing capacity, it's been analyzed by many researchers, including Skempton, and then approximately it is 5 something. Therefore, it is given by the equation, empirical equation D. So QF is equal to CNC, where NC is approximately around 5. Therefore, pi plus 2 is 3.14 plus 2, approximately 5.14. So answer is D. Yeah. I want you to answer this question. 4 columns of a building are to be located within a plot size of 10 meter by 10 meter. Please note 4 columns. So plot size is 10 meters here and 10 meters in the other direction. Expected load on each column. Each of this column carries a load of 4,000 kilonewtons. Allowable bearing capacity SBC QS is equal to 100 kilonewton per meter squared. What type of foundation is best suited for it? Okay. First thing, let us consider, anyway, more on this we will talk little later. However, I have this problem here, therefore, let me answer this, and then, we'll go deeper later on. Each of the column carries 4,000 kilonewton load. Assume that you are going to put isolated footings. Then, for 100 square meter, 100 kilonewton per meter squared SBC, and when the area of plot is 100 square meters, you will notice that for each isolated footing you require 40 square meters. Why 40 square meters? It is the total load divided by SBC. Total load is 4,000 kilonewton. SBC is 100 kilonewton per meter square. So that's equal to 40 square meters. If there are 4 columns, 4 into 40, 160 square meters. What is the area given? 100 square meters only. 10 by 10, 100 square meters only. What you require is, much more than that. Therefore, it is not acceptable, isolated. Next, you go for raft foundation. Total load is 1,600. SBC is 100. And hence area required is 160 square meters, which is also more than 100 what you have. Therefore, it is also not acceptable. Combined footing, no chance. So none of the shallow foundations are acceptable. So only solution is go for pile foundation. That means, you're going to transfer the load at greater depths than at shallow depth. Therefore, you need to go for a pile foundation. Okay, let me answer the next question. An embankment is to be constructed with a granular soil. That means, sandy soil. Bulk unit weight, bulk density is 20 kilonewton per meter cube. On a saturated clay silt deposit, okay, the undrained shear strength is given as 25 kilopascal. You conduct that in unconfined compression testing machine. Therefore, you can simply say that C cohesion is half of undrained shear strength, that is 25 by 2 kilopascal. Assuming undrained general shear failure, so assuming that it experiences general shear failure, and bearing capacity factor 5.7, the maximum height, okay, QF is equal to, in this case, it is embankment, therefore it is like strip footing, simply C into NC. NC is given as 5.7. C is equal to 25 by 2. Therefore, 12.5 into 5.7, and that is the bearing capacity. Okay, that's the bearing capacity of soil. And now, how much load you can apply on top? That is given by gamma times Z. Gamma is 20 kilonewton per meter cube. That is how the embankment is filled at that density into Z. All other things known, only Z is to be determined. Z is 3.56 meters. So you can load with the embankment material compacted like this for a depth of 3.5 meters. Anything more than that, it is likely to fail. Okay, let's see here. Likelihood of general shear failure for an isolated footing in sand. In sandy material, general shear failure is seen when, number one, soil is dense. The relative density is fairly high, 70% and above. Two, when the soil is at shallow depths. That is, when the depth of foundation is small. In that case, general shear failure is seen. Likelihood of general shear failure in isolated footing on sand decreases. The chances decrease when you see which is the best answer. There is decrease in depth of footing depth. When you decrease, it becomes more likely general shear failure increases. A is not acceptable. I'll go to C now because I have written answer as B. Increase in the footing width. When you increase the width of the footing, it is decreasing the depth only. So in that case also, general shear failure chances increase. So C is ruled out. When you decrease the soil grain compressibility, so soil grains are, compressed. When you decrease the compressibility, when it is loose, okay, then when you decrease that this one, there also chances are not there. Only when you decrease the intergranular packing, that means when the packing is reduced automatically from general shear failure, it is possible that it goes to local shear failure. So answer to this is B, and you have to carefully read the question, carefully read the answers, and normally one or two answers can be easily eliminated. You may have confusion between any other two. You have to guess carefully. Okay, friends, let us move forward. We have talked enough on bearing capacity. Why bearing capacity is required? Because you need to design foundations. Let us try to see the different types of foundations. Very broadly, you can define this, you can categorize foundations into two types. One is shallow foundation and the other one is deep foundation. When do you call a foundation as shallow? This one is a shallow foundation. The depth of foundation is smaller than the width of foundation, or depth to width ratio is less than 1. Under this case, you can call the foundation as shallow. What do you do in shallow foundation? Whatever load the foundation carries, you assume that it is transferred at the base of the foundation. The soil at the base, resists the load. What happens to the soil? We assume that this soil does not exist at all in the neighborhood. Strictly, that's why I said assume. It's not correct, but we assume like that. Because the depth of foundation is shallow, this assumption is okay, acceptable. You're on the conservative side. Okay. Under these conditions, you say that it is a shallow foundation. Depth to width ratio less than 1, and the in the neighborhood presence of the soil is neglected. Which are the different shallow foundations? Different types. You have wall footing, you have isolated footing, you have combined footing, strip footing, mat or raft foundation. I have put them in an order. Isolated footing is the simplest, easiest. Mat is perhaps the most complex of the shallow foundations. And naturally, which foundation you should go for? You should always go for the simplest. Why? A simplest foundation is less costly. It is economical, easy to construct. You don't require, sophisticated equipments. You don't require too much of labor also. You don't require, high technology. That means, the experts also complicated, conditions one need not bother about. Sophisticated experts are also not required. You don't require, very good ground investigation. You don't have to take the investigation deeper. So, given a choice, you always prefer a shallow foundation. Only when that is not possible, you go for an alternative. So, that alternative comes from deep foundation. So, when do you call a foundation as deep? When the depth is very much larger than the width of foundation. When the depth is very much larger than width of foundation. How large? As per the definition, df by b is greater than 1, but normally df by b may be greater than 5, greater than 10, sometimes even greater than 50. You may have the pile foundation more than 50 meters long. Diameter of the pile foundation may be 0.75 meter or 1 meter. So df by b can be even more than 50. Which are the popular deep foundations? Pile foundation is the most popular deep foundation. In many of the waterfront structures, okay, you may use Kaizen or oil foundation. And today, we talk about pile raft foundation. So what is pile raft foundation? So it is a combination of pile and raft. Pile foundation definitely has a pile cap. We don't assume that, pile cap resists the load. We don't even intend to put the pile cap on the soil. We say that, it is above the soil. Whereas, in pile raft foundation, you put the raft on the ground. So some of the load is taken by raft, some of the load is taken by pile, and hence, total load carried is equal to load carried by pile plus load carried by raft, particularly for tall towers carrying enormous loads. This is a popular type of foundation these days. It is more economical than pile foundation because in pile foundation you don't consider the the presence of pile cap. Okay, but in pile foundation, therefore pile cap here will become a raft. So raft will take some load, and hence load on the pile will decrease, and hence number of piles can be reduced. It becomes more economical. So let's try to see shallow foundation. As I said earlier, it is the most common foundation, most wanted foundation also. Given a choice, we should prefer shallow foundation. When do you go for shallow foundation? Two important reasons. The structure is not very complicated and not very heavy, simple structure. And second most important point is, at the shallow depth, the structure, the soil is very strong. having good bearing capacity. So at shallow depth, soil is strong, and then the structure is not very complicated. It doesn't carry very heavy load. When do you go for deep foundation? So, two important reasons. When the soil structure is very complex, okay, structure is complex. Two, when the soil near the surface is poor, so you take the foundation deep up to stronger soil like bedrock. Naturally, it may be more expensive. It may require, sophisticated equipment, expertise, good expertise, lot of time is required, and so on. But you can use pile foundation, which is a deep foundation, to solve problems like this whenever you have a weak soil near the surface. So these are some of the typical shallow foundations. Here you see isolated footing, elevation, plan. Combined footing, elevation, and plan. Here also, combined footing. Only difference between this is a rectangular footing and this one is a trapezoidal footing. Then you have strip footing. When you have a number of columns in one row being connected together by one single foundation, you call it as strip footing. Then you have strap foundation. What do you do here? You have one isolated footing here, you have another isolated footing here. You don't leave them like that, you connect them together by a rigid beam. So this is a strap footing. This beam is called strap. Then you have mat or raft foundation. This is the complete shallow foundation. You have a number of columns, number of columns in both the directions connected together by one single foundation, and hence you call it as raft foundation. So this is perhaps a complete shallow foundation, most expensive of the shallow foundations. So you provide this when others do not become feasible. Okay, let me ask this question now. I'm sure you will not have difficulty in answering. A foundation is said to be shallow. When will the foundation be shallow? When do you call a foundation a shallow foundation? When, number one, depth of foundation is smaller than the width of foundation. So here, depth of foundation is smaller, less than the width of foundation. Number two, foundation extends to shallow depth only. So the foundation here is up to shallow depth, maximum 3 meters, much less than 3 meters. Presence of neighboring soil is neglected when, in a foundation, only the load is considered to be shared at the base. The neighboring soil is considered to be absent. All the other cases are satisfied. So naturally, this is one condition. The depth should be shallow. This is the other condition. Neighboring soil does not take part. This is the third condition. Since all these three are satisfied, the answer is D. So this is how you can answer, friends. Okay, I have another question for you people. Pick a shallow foundation among the following. Pick a shallow foundation. Very simple. Pile foundation, deep foundation. Therefore, it is not acceptable. Well foundation or Kaizen, deep foundation, not acceptable. Pile raft foundation, it is raft as well as pile. Therefore, it is again deep foundation. So the answer is raft. So only single answer is raft. Acceptable answer is raft. Okay, friends, let us spend a little time on talking about different types of shallow foundations. Sometimes you will have some numerical problems on it. One of the most important things is, proportioning the foundation. What do I mean by proportioning the foundation? You try to distribute, plan the type of foundation, and you distribute the area of foundation. So no structural thing here. So it is a geotechnical problem. So note down here, let us say you have the load coming equal to 1000 kilonewtons. So load from the superstructure. Let us say you have to design a column, you have to put a column, and you know that the column is subjected to a load of 1000 kilonewtons. Okay. A pressure of 1000 kilonewton, the force of 1000 kilonewton. You have a foundation here. Assume that the foundation is 1 meter in width, 1 meter in depth. So entire load is transferred to the soil. At the base here, the pressure on the soil is total load 1000 divided by whatever is the area of the foundation. So 1000 kilonewton per square meters. Let us say the capacity of the soil is not 1000, very much low, say 300. Then what happens? Its capacity is 300 kilonewton per meter squared or kilopascal. But you are applying 1000 kilonewton per meter squared, much more. Just imagine you have a weightlifter who can maximum lift about 200 kgs. You give him 50 kgs, he will lift easily. Give him 100 kgs, he will lift. 150 kgs, he will lift with some difficulty. Even up to 200 kgs, he may lift with great difficulty. But if you give him 250 kgs, 300 kgs, he will never lift, he will collapse. Likewise, the soil below the base of the foundation will collapse in this case. That means it fails. Once it fails, soil is a clever material. It says, okay, now I have failed, therefore I don't carry the load. What will happen? It will ask the neighboring soil to take the load. So when you apply the load, when the soil fails, that soil will simply transfer all the loads to the neighboring soil. So neighboring soil is overloaded, overstressed, it fails, it transfers to the next one. So likewise, progressively failure happens. So what should you do? You can't provide a pressure equal to 1000 kilonewton per meter square. One way to reduce is reduce the load itself. Instead of 1000, you put it as 250. But our architects or our user, whoever is the user of the space, they say nothing doing. I want it 1000, do whatever you want. So what we do, we design the foundation. We provide a rigid foundation here in such a way that the pressure below is reduced to less than 300 kilonewton per meter squared. So instead of providing 1 meter by 1 meter, you provide 2 meter by 2 meters footing. Same load, 1000 divided by 2 by 2, the pressure reduces considerably to 250. And hence, the capacity is 300, but pressure is 250. Therefore, the foundation soil is safe. This is what is proportioning of the foundation. Well, friends, I just want you to understand that it's always better to go for simple foundation. That means, given a choice, we'll go for isolated footing. For every column, one single foundation. But not always you'll be successful. You may have to yield, you may have to change. Let us see when we change to combined footing. What is a combined footing? You have one column here, you have another column here. You cannot provide isolated footing like this. You cannot provide isolated footing like this. Instead, you're going to combine these two put together and put one single foundation. So when do you provide combined footing? I have written down, some of the important factors which influence the, foundation engineer, geotechnical engineer to decide on going in for combined footing. Property line restriction, overlapping of stresses, scale of differential settlement, importance of the structure, and designer's wish. I take you one by one onto each of them. First one is property line restriction. Let us say that, this is the boundary of your premises. Your architect says that He wants a column here. Where? At the boundary. And we have to yield to the architect. Nothing doing, you have to put the column here. So one way to put is, after all below the ground, therefore you put an isolated footing in such a way that, the column is central like this. So what have you done? You have gone into the neighbor's land. Maybe below the ground, but you have gone into the neighbor's land. Is it possible? Well, if the neighbor is a no, please excuse me, sir ನಾನು ಗೇಟ್ ಟ್ರೈನಿಂಗ್ ಕೊಡ್ತಾ ಇದ್ದೀನಿ, ಆಮೇಲೆ ಮಾತಾಡ್ತೀನಿ. ಓಕೆ ಸರ್, ಓಕೆ ಸರ್. So you just cannot do it because you have no right to occupy your neighbor space. Many structural engineers decide on something like this. You have the column here, and they say, you put the foundation. I mean, you put a rigid beam here. You also can put a rigid beam here. It's not going to help because when you take a situation like this, the entire load is eccentric, maximum on this side, and it may be close to zero or it may even be lifted up. Therefore, there may be separation. So these two are never acceptable. So whenever a situation arises when you need to put a column at the edge of the property line, you are advised to consider one more column next to it. Even if it is not there, you can have a dummy column. Preferably provide a column and then connect these two put together and have one single foundation, which is a combined footing. More than 40 to 50% of the times, a designer goes for combined footing for this reason. Let me go to the next reason, overlapping of stresses. What do I mean by overlapping of stresses? You have a footing like this carrying the load of the column. Below you have the soil, which is particulate in nature. Whenever you are transferring the load transfer is through bearing, and hence it spreads like this. Okay, the load transfer always is spread at some angle here, at some angle here. If it is a very stiff soil, the angle is small. Maybe in rock, you may not have a spread like this, but in particulate material, load dispersion always takes place like this. And in a softer soil, with respect to vertical, the angle becomes flat. Okay, with respect to vertical, this angle becomes large. Okay, so now assume that you have two columns close by, two foundations close by. The gap between them is less. So this foundation has the load spread like this, and this foundation also has the load spread like this. So what is the problem? I told you about the pressure below. So if let us say this carries 1000 kilonewton, area of this is 2 meter by 2 meter, therefore the pressure here is 250. Here also same, let us say, and the pressure here will be 250. What about here? At this point, from here it is close to 250, from here it is close to 250, total will be very close to 500. So there is scope for this portion to fail, and once it fails, things are gone. So you have to see to it that whenever there is a scope for overlapping of stresses, whenever you have the two of the foundations close to each other, very close to each other, instead of two foundations separate, you combine them and put one single foundation. That is the best solution. So whenever the column loads are heavy, spacing between the columns is less, soil has very low bearing capacity. In all these conditions, in all these situations, the value of the spacing between the two footings is small. So don't go for isolated footings. You need to go for combined footing. The other important reason, So the second reason which I mentioned, overlapping of stresses, also takes up to 40 to 50% of the cases. So chunk of the decisions of combined footing are made because of the first two reasons only. Sometimes, soil, I told you, is inhomogeneous, anisotropic. There is a possibility that one below one column the soil is soft, below another column soil is more stiff. There is a possibility that load also is not uniform, or maybe below two column soil is fairly stiff, but in between, somewhere in between, soil is very soft. So in those cases, the designer will take a decision to go for a one single combined footing. What is the advantage? If you go for isolated footings, maybe one footing may settle much more compared to the other footing, because the soil doesn't have uniform properties. The loading is also not uniform, causing differential settlement. Friends, differential settlement is very bad. That will put a lot of pressure on the joints between the beam and column. So you need to stop, you need to avoid as much as possible. So one simple way of solving that problem is combine the foundations together. Then one portion it may try to settle more. So this portion may try to settle down, but then it says combined foundation, therefore it doesn't allow. Slight settlement, slightly more settlement may be there, but it will be very much less than a situation when you have two isolated footings. So whenever you have this care of differential settlement by providing two isolated footings, you decide and go for a combined footing. The other important thing I said as designer's wish. Okay, one more thing I forgot to mention here: importance of the structure. Let us say you want to build maybe Parliament House. You want to build Rashtrapati Bhavan, Vidhan Sauda. Naturally, the structure is very, very important. Naturally, people who live in that, who work in that, are very, very important. So in that situation, what does the designer do? He looks at the kind of soil, and then oh, soil is very strong, no problem. Then he thinks twice whether to provide isolated footing. Why he take risk? Let me just go for a combining these two and have a much safer one, combined footing or maybe mat foundation. Many a times, when the structure is important, designer does not want to take risk. He always wants to play safe, and hence he goes for a higher order foundation. That's another instance when a designer will probably go for a combined footing. So this is another interesting thing, because of the designer's wish I have mentioned. What do I mean by this? You know, okay, let us say you have a portal frame. Let us say you have a symmetric portal frame. So under this column, you have to provide a footing. This column carries an axial load and a moment. An axial load, say P, moment M. What about here? This column also carries an axial load P and moment M. Because of symmetry, this is P, this is also P, this is M, this is also M. Most of the times you may have realized if this is clockwise moment, this one is anti-clockwise moment. Now, try to design an isolated footing. Try to design an isolated footing for this. What happens? You have to design for the axial load and the moment. Try to design another isolated footing for this. So, axial load and moment. So, you have to consider the moment also. Just imagine you're going to combine these two, put one single foundation. What is the advantage? This moment M neutralizes with this moment. One is clockwise M, another is anti-clockwise M. Therefore, you don't have to consider the moment at all. You only do for axial loads. So designer wants to cleverly reduce the problem on him. Reduce, taking the moment effect and other things. Or maybe sometimes you have a horizontal force here, H, you have another horizontal force H in the other direction. So by combining, you can neutralize these two. So this is when the designer again thinks of going in for a combined footing. So friends, you should have an idea as to when to go in for a combined footing. And it is very, very important that the designer plans systematically. Please note, combined footing is costlier. It requires more work. But if the situation is such that isolated footing is not feasible, you have to go for combined footing. Yeah, I have a question here. Let me see whether you find it easy to answer. I didn't tell you when you go for a trapezoidal combined footing. You know, when the two columns are unequally loaded and at the edge of heavier column, you want to stop the footing due to some reason, maybe this is the edge of the property line, then the best possible combined footing is to provide a trapezoidal combined footing. Why? Maybe the question itself will answer. You have a combined footing, combined trapezoidal footing of length L, supporting two identical square columns of size 0.5 meter by 0.5 meter. The columns P1 and P2, this column is 2000, it carries 2000 load, whereas this carries 1500 load. If the stress beneath the footing is uniform, the stresses below the footing, you want them to be uniform. You find the length of the combined footing up to 2 decimal places. Please note, whenever you want the pressure to be uniform, you have to see to it that the CG of the load, the two loads, should coincide with the centroid of the area of the trapezium. Only then, you can have the pressure uniform. So, applying this concept, you try to find the distance of the CG of these two columns. Naturally, this is heavier column, CG lies closer to it. What is the distance? From the edge of this heavier column, it is 0.25 meter here, plus, you apply Varignon's theorem. Moment of the resultant is equal to sum of the moments of the other two forces. So you get this answer. And this is the CG of the load. Centroid of the trapezium, if I call this as A, if I call this as B, then from the A edge, the distance is A plus 2B by A plus B into L by 3, where L is the length of the combined footing. And these two should be equal because, I said, the concept is that the CG should coincide with the centroid of the area of the footing. So based on this, everything is known, A is known, B is known, the two loads are known. You find out the length, and I found the value of the length as 5.83 meters. So this is how, friends, you can probably design, proportion a combined footing. The challenge there is to find A, to find B, and to find L accordingly. The objective is to see that the CG coincides with the centroid of the area of the foundation. And sometimes, if it is not possible, you'll have to consider the extra moment. That means, pressure is not going to be uniform. Okay? Well, I can speak now, on the situations, okay, which promote a designer to go for raft foundation. Well, all those situations which promote the designer to go for combined footing hold good here. In addition, you need to consider perhaps, the effect of the groundwater table, perhaps the underground cellars, or maybe the settlement criteria. Probably we will discuss this in my next class. I think it is time for us to stop because I need to tell you today we solved a number of problems related to Terminologies bearing capacity theory. And then we moved to the higher order bearing capacity theory. So Meyerhoff's bearing capacity theory, I explained to you. Likewise, you can take Wesig's theory, you can take Bella's theory, doesn't matter. Okay, they consider more factors into account. So we then talked about the one given by Meyerhoff. You can call it as generalized bearing capacity theory. It takes into account more factors. We solved a number of problems there also. And then moved over to talking about shallow foundations. So I talked about, different types of foundations, shallow and deep. When do you call a foundation as shallow? When it is deep? Which are the different popular shallow foundations? Which are the popular deep foundations? And then started explaining about shallow foundations. Finally, I said that simplest foundation is always good, but when it is not possible, you go for a higher order foundation. I very clearly explained to you when you go for a combined footing instead of isolated footing. Maybe in the next class, we'll continue from here and see when you provide the raft foundation and go ahead. I stop here. I thank all of you for your patient listening, and let us look forward to, okay, let us look forward to my next class in the immediate future. Thank you, friends.
Thank you, sir. It was a very informative session. Hope all the participants are clear with the concept. Next session will be on Monday. We'll see you on Monday. Thank you, everyone.